All right, so just trying to throw in some review things here as we look forward to the midterms next week. So you got position, velocity, acceleration. That's F prime, F double prime, right? Relationship. They give you velocity here, so ask about acceleration. So basically, that's the derivative, the slope of that. Whenever we have a table of values, about the best we can do is slope between 2 points. Hopefully, 2 really close points would be the ones we'd want to pick. And so if we're doing t equals 4, which would be in between here, best we can do is a slope between those 2 points. So 10 minus 6, 5 minus 3, 4 over 2 is 2. And then the units would match up, of course, because this is meters per second. That's the other thing you really should pay attention to, is make sure those units are matching. You wouldn't want one to be seconds, one to be minutes. Then you would have to do some adjusting. So you should always pay attention to that. But since they do match up, you got meters per second over seconds, which is meters per second squared, or acceleration, whatever. Okay, so simple little thing there, but you know, we want to be able to do the simple things. Okay, I got a couple of these to do here today. Let's look at this one. This one take a little bit more time, probably. A little more calculating. Go ahead and give that a try. If you want to talk about it with each other, whatever, that's fine too. But if you need a little help, if not, be good to do it on your own too. So one of those related rate situations, right? Like the quiz we had, these show up a lot in the multiple choice section, typically of the test. Not so much in the free response part, and partly I think it's because the free response part has multiple parts to it. These problems are pretty much usually just one thing. Now, I have seen problems where they would ask a variety of questions in a problem, and then you have different parts, and then one of the parts is, how fast is this variable changing, when this variable and this variable are whatever. And so sometimes it's a part of one of the free response questions too. But you have one of the snowmen walking south, one walking east. Now I always do get questions, or sometimes people wonder about this, if this should be negative because it's going down, right, in the map, but it's not, right? It's not negative. Why? Because what's y doing? Increasing. This distance is increasing, so therefore y prime has to be positive. And x is increasing, so x prime has to be positive. So that's 2 and 4. So we set it up this way. They're all changing, so do the derivative with respect to t. So we do get an x prime, we do get a y prime, we do get a z prime. I just divided the 2's out of there then. The 2's would just all divide out, so just to make it easier. But then I don't know x, y, or z. How can I get that?
It would give you up to 3 hours. So you can put that in.
That's the key, right? So 4 miles an hour going south in 3 hours, so that means y will be 12. And 3 hours at 2 miles per hour, that's going to be 6. So x is going to be 6. So you can put those back into here. 6 squared, 36, plus 12 squared, 144 is 180. Square root of 180 would be the z. So back to this. So for my x, I could put 6. For my y, I could put 12. For this, I could put square root of 180. That's a lot like that baseball problem we had in the last quiz, right? And so we get 12 and 48, which is 60. So 60 divided by root 180 would be your z prime, and you could leave it like that. That'd be fine. Or what would it come out?
2 root 5.
2 root 5, or maybe do decimal 472 or something like that. But all those would be a 2 root 5. 4 or 5 root 2 or whatever you said it was. 4 root 2, I get 2 root 5, 4.472, whatever. Units would be good. It'd be miles per hour. That would be good also. This is even okay, right? Even though that's probably not what we consider simplified for a problem like that, that'd be okay. Now, if it's a multiple choice, obviously you're going to have to match your answer to what it was. If it was a no calculator, then it'd probably be in radical form. If it's a calculator one, probably be a decimal. Okay, let's do one more here. Let's take a look at this one. Okay. Give that one a try. So if you're stuck at all, the hint I would give you is before you can find h prime of 30, you need h prime of x, right? Before you can find h prime of 30, you need h prime of x, right? what do we got?
Take it, change it.
50? 50, okay? Because the key is that line right there, right? Chain rule. You got H is equal to F of G of X, so H prime of X would be derivative of the outside, F prime, leave the inside alone, G of X, times derivative of the inside, G prime. And then you substitute your 30 everywhere you have an X. So it would be F prime of G of 30 times G prime of 30.
If
Right.
there's like a 2x in there, would you multiply out as
2X in here,
2? Yeah, like so, like.
Yeah. So that'd be F prime of G of 2X times G prime of 2X times 2, right? And you kick out the derivative of that inside. Okay? So starting on the inside, G of 30 would be right here, that'd be 20. So 20 would go inside here, so you'd have F prime of 20 times G prime of 30. F prime of 20 is 5, and G prime of 30 is 10. So 5 times 10 would be 50. Okay, so just like that, using the chain rule. All right. Let's see. No. Okay, so let's do those. All right, so your practice exam, sample 1 or sample 2, let's try to finish those up, or at least the questions on those. We'll move on to that next one. Now these two sample ones will be due on Wednesday when we take our first midterm. And then the other 2 packets we will hand in on that Thursday of that one. Okay? Yes.
Could you, on like the last part of section 2, part A, could you do 3?
On sample 2?
Sample 2, probably 3 and 4.
And 3 and 4 and 5. Well, I don't, let's see, in the other class we worked through 3, we worked through a lot of 4, and we could probably do that one, and this is 5. Oh, 5. 5's easy.
No, you're right.
Just kidding. But I will definitely, when we have some work time, and we will have some work time on these various days, I will definitely help you individually with some of these. Please ask on some of this. We won't have time to go through all of them, but all together. But I will help you with whatever ones you want to. So there are several things that would be pretty good to talk about with 3 here. Because one of the things 3 is, now this says a calculator can be used. I would say that now most of this problem would be more no calculator. These packets are fair, a number of years old. And a few things have changed, not a lot has changed, but a few things. One of the things that's changed is the CAS, the computer algebra calculator, which can solve. So we can do some stuff even with the B, right? Like if I wanted to set this equal to 0x cubed minus 3b, I'd have to put a time sign between the b and the x, but and set that equals 0, solve in terms of b, it would actually do it. The calculators and graphic calculators a number of years ago didn't do that as much, and so they would put this in a calculator part, knowing that people would have to do many parts of it without a calculator. But now with these, that kind of changes that. So I think most of this would be a no calculator problem, so I'm going to treat it that way. Now this part wouldn't be. So if this was a no calculator, they probably wouldn't ask you this first part where they wanted you to do this graph. So if I put in a 1, a 2, a 3, and for b, I get 3 different cubics. And one of the things you probably noticed if you went ahead and did that is one of them looked kind of like this, then the other one kind of came up and did this, and then the next one kind of came up and something. Well, that's terrible. This one's kind of in here, whatever. And actually what I want to show you in part D, then in part D it says show that the max and mins, relative max mins the same as local max min, all lie on this curve. And it's actually kind of cool because what happens is if you take all these maximums of all the different ones in this family, if you will, of functions, for all these different b values, you get a whole bunch, and every time you change b, you get another curve. And if you were to connect these, they actually connect on a cubic that would actually be this right here. And then what they do in part D is have you find the a value, which we'll get to in a minute. But it's kind of neat. And that cubic, there's a cubic equation that actually connects all of the different max and mins of this other cubic set of cubic equations. All right. So anyway, that was part B. So if we go into part A, part B and C is talking about finding the relative, which means local, right? So local max min. Now, in terms of B, means, and Trey, we had this conversation yesterday, it's not with respect to B, it's in terms of B, which means there'll be B's in your answer. That's what that means. So there was the one we were talking about, I can't remember which one it was for sure, but if you had something like this, and it said find D, don't write this down right now, but if it said find dy dx in terms of y. Okay, now what that's saying is find y prime with respect to x, but your answer will have y's in it, is what that's saying. Okay, so what you do, of course, when you do that derivative, be 2y, y prime, plus 2 equals y prime. Now, there's no x prime, remember, because we're doing it with respect to x. So, therefore, it'd be x prime would just be dx over dx, which is 1. But anyway, when you finish this problem, get the y primes together, move that over there, factor out a y prime. This is your implicit differentiation stuff. At the end of the day, you would end up with this, and so that means in terms of y, right? It's got y's in it. Okay, so understand the difference between with respect to y or in terms of, right? So this says our answer is going to have b's in it, is what it's going to have. All right, so they gave us this equation, y equals x cubed minus 3bx, and we're supposed to find the local max min. So forget the b, because that always throws us off when we have a b or a k in there. Just treat it like any number. Now, it does make it a little trickier, but you just have to think like you would if it was any just regular equation. What do we do to find a local max?
Do the derivative.
Do the derivative, set it equals 0. Now, we already know what y looks like, so we're a little bit ahead of the game. I'm going to kind of pretend I don't know this. I mean, we'll use it, but I'm going to work it like I didn't already know that there's going to be one local max and one local min. So I know I'm going to have one local max and I'm going to have one local min because I've already seen what the graphs look like in part A. Okay, and the local max is going to come first and the local min is going to come second. So I already kind of know that, but it's possible that maybe I wouldn't have known that. So what I would do is look for where the derivative is 0. So we have y prime equals 3x squared minus 3b, right? 3b is just a number in front of an x. That's the derivative. I want to set that equal to 0. So I'm going to solve that. So I get 3x squared equals 3b. I get x squared equals b. I get x equals, don't forget, plus or minus square root of b. Well, that tells me I got 2 stationary points, which I knew I was going to get. I know the first one's going to be my max, so I really already know. They want the x and y coordinates. I already know that my max is going to be that one. I just know that from the picture in part A. I know the max is going to be the first one, and I know my min is going to be the second one, the positive one, right? So if I was working this one, and I'd already drawn those graphs with my calculator, then I would probably at this point just say, because notice it didn't really say justify or whatever. Now, I would always, there's my grade on the line, and I was doing a free response question, and I know you're getting graded for doing this, and so forth. I would justify, right? So I would say something like I just said, I know because of part A, the local max is the first first stationary point, and the local min is the second stationary point. So therefore, that one is the local max, that one's local min, and so forth. Now, all that's really left is to do what? Plug them back into the original for x, right? And see what we get, okay? Now, I want to do more than that right now because this, I know, I've seen this come up on the midterm before, the final, or in other packets, whatever, where you do have to justify and figure out which one's the local max or min, right? So let's pretend we didn't know this graph existed, and we don't know which one of these is a local max or min. What would we do? What do you do for a local max min? Well, you stick what in?
Do the number line.
The number line, right? The number line, and then put those things into the derivative. So let's do that, because it's a little bit different when you have these b's. So I'm going to do a y prime number line. I'm going to put negative root b here, and I'm going to put root b here, because I know b's positive. They told me that, I think, in the original problem. B was positive. Okay? So it's easy. What's a number in between? 0 would be easy. What about a number that's bigger than square root of b?
Just B infinity.
Just b. What if b is 1/4? Is 1/4 bigger than square root 1/4? What's square root 1/4? 1/2. So b is not necessarily bigger than square root b. I know we think when we do a square root of a number it makes it littler, but it doesn't. Not if it's less than 1, right? All we know is b is positive. We don't know if b is greater than 1 for sure. So you got to be careful on that. Squaring a number, a lot of times people think squaring a number makes it bigger. Squaring a number does not make it bigger. Not if it's less than 1, right? If you take 1/4 and you square it, you get 1/2. No, I said that right, I did square root. If you take 1/2 and square it, you get 1/4. You get a littler number. Okay, so squaring a number does not necessarily make it bigger. Square rooting a number does not necessarily make it littler. So, what would make square root of b bigger? How about we multiply by 2? That will always make a positive number bigger if you multiply it by 2. And likewise, if we needed something littler than square root b, for example, what if 0 was one of our stationary points and we needed something between 0 and root b? 1/2 times root b would be the good choice. We would know that would be littler than root b. Okay, and then what would be to the left of negative root b? Negative 2 root b. Okay, so that's a little thing that will come in handy for you down the road. I know that will happen in some other problems that we do. Okay, now I plug those back into where?
The derivative.
The derivative, which would be right here. Okay, so let's do 0 first. That's easy. 3 times 0 is 0. 0 minus 3b, that'd be negative 3b, but remember I know b is positive. So that's negative, right? Negative 3 times a positive is going to be negative. Okay, let's put 2 root b. Now again, I'm pretending I don't know this graph. So I'll put 2 root b in here and I square it. What do you get when you square 2 root b? Well, it's positive, but we need more than that. 4b. 4b times 3, 12b minus 3b, 9b, which I do know that's positive, 9b. Okay? And then over here, I take negative 2 root b, and I plug it in, I square it, that would be 4b, well, same thing. Times 3 is 12b, 12b minus 3b would be 9b, which is positive. Okay, so now then I would have, and then remember our old justifications, we said since f prime, or y prime in this case, is changing from positive to negative, then y is changing from increasing to decreasing, so we have a local max at the first one, we have a local min at the second one. But that's a little bit of when you have those b's and stuff and you want to put them in a number line or a k or something like that, or an e or, pi sometimes, whatever, even though those are numbers, but we just work it the same way. Okay? So especially if this was a no calculator thing. All right, now, like you said, we're just going to plug these back in here. Now, it gets a little tricky here, so let's plug this in. So we're going to go y, we're going to put negative root b cubed minus 3b times negative root b. Right? So I'm plugging this in to get my y coordinate. A lot of times we don't want that, right? When we do local max min, a lot of times we just want the x values, right? But this particular time they want the x and the y. So it's almost like listed candidates a little bit. We're putting it back into the original to get that value. So this is b to the 1/2 to the third power and power. You multiply, so that'd be, and then negative cubed is still negative. So that'd be 3 has power, right? And then this would be b to the first, b to the 1/2. You add the powers. That's also 3 has power, but it becomes plus 3b, 3 has power. So since they have the same power, we can add them. Like x squared plus x squared is 2x squared, right? So we can add negative 1 plus 3, which would be 2. So this would be 2b to the 3 halves. And it doesn't surprise me to get a positive, because if we look at our graphs in part A, it was a positive y value. Okay? Now I'm going to put in root b into there.
Isn't that the same thing as 2b times square root b?
No. It'd be the same thing as 2... Yeah. Oh, yeah. Yeah. 2b square root of b. Are those the same?
Yeah.
Yeah. And I think that would be fine. That would more be just kind of simplifying. I suppose technically I'm not sure I'd want to do it, but could you leave it just like this? They do talk about how you don't really need to simplify it arithmetically or algebraically for final answers. So my guess is, to be honest, if you really weren't very confident in being able to simplify this, if you just put that as your y value, most of the time on the AP test, you probably get that point. Okay, so that's not bad. All right, or if you left it like this, that'd probably be okay. Now, other times there are reasons why you want to be able to simplify it to go on further. So, not a bad thing to be able to do that. Okay, so here we'd have root b cubed, so that would be our b to the 3/2 again. And then minus 3b times root b, which would be 3b to the 3/2. So this time it'd be 1 minus 3, so it'd be negative 2 b to the 3/2. It doesn't surprise us because there is going to be a symmetry there probably on that cubic. So it doesn't surprise us that we would get that. Okay, so those are our local max and our local min, but it's made trickier by the fact that we're working with all those b's in there. And then on D, this part I think is kind of cool then, is it says those max and min points all lie on this right here. Well, here's our local max point, was negative root b, 2b to the 3/2. So how can we show that those points are on this?
Plug them in.
Plug them in, the x and y, that's what I mean. This is actually the easiest part. Now, if you didn't get B and C, obviously you don't have anything to plug in here, but that's where you can take wrong answers and still get some points. Like, for example, if you came up with something as your values for parts B and C, but they were wrong, but then you came down here and actually plugged them in for the x and the y and then tried something, you might get a point. There might be 1 point for plugging your max point. They actually say that in their grading notes. They'll say the student gets 1 point for taking their max and min points from the previous part and plugging them in for the x and y here. Okay, that could be worth 1 point. All right, so anyway, so we get 2b to the 3/2 here equals negative a, and then x cubed, that'd be negative b to the 1/2 cubed, which we already said that'd be a negative, and that'd be b to the 3/2, so this would turn to positive a b to the 3/2, 2b to the 3/2, those would cancel, we get a equals, I feel like I'm missing a 2, we get a equals 2. Yeah, no, I think that's right. Now, what that means is, and if you actually had done this problem, if you had done this and you still have those cubic graphs in your calculator, those 3 cubic graphs from part A, it's kind of cool to go ahead and put this in right here, and you should see it go through all those, it'll go through all the max and min points of that. Okay, by putting that 2 back right there. But anyway, that was probably a 2-point part right there. My guess is you got a point for plugging your x and y in, and then a point for getting A is 2. Okay? All right. So that's a little tougher one. You can expect, though, I mean, that's a chart thing, local max min, doing a number line. You can expect to have to do that probably a few times somehow in the quiz, for sure, because that's a big part of what we learned with derivatives and doing. This would be a harder version of that, but there'll probably be some easier ones too. Let's talk about this one, because differential equation is something that always kind of tricks us a little bit, but they do some of it for you, like they show you what the solution is. Remember, the solution to a differential equation is the original function, which they give you here in part A. But this one does have something kind of interesting. They said, first of all, this is the differential equation for all x not equal to 0. Because obviously you put a 0 in here, it's undefined. Okay, so this is the differential equation. This is the y primes, as long as x isn't 0. Okay, then they say, here's a solution where x can't be negative c, which again would give you a no solution, or a undefined point on the original graph. Here would be an undefined slope. Here would be an undefined point. But then it says, show that all solutions contain 0, 0. So we just got in saying up here that x can't be 0. Well, that just means x can't be 0. If x is 0, then that y prime doesn't apply. If x is 0, this y prime doesn't apply. But x can still be 0 on the solution. So that's what we're going to take a look at here in part A. Okay, so part A, verify. How did we do that with verify? Well, that was involved, but it was that T chart kind of thing, right? So here's our y prime, and we kind of did this. Okay, so in place of y here, I'm going to put x over x plus c minus, and then I'm going to do y prime, or excuse me, y squared. So I'll square the top, square the bottom. So that would be this, right? So that'd be y plugged in there. That'd be y squared plugged in there, and then all over x. So that's the right side. The left side needs to be y prime. So I need to do, let me rewrite this over here. So I need to do the derivative of this right here. So I would do the quotient rule because I can tell it's going to be pretty easy. Derivative top is just going to be 1, derivative bottom is just going to be 1. So I can tell the quotient rule will be pretty easy. Instead of flipping that up and make it negative 1 power, I think it would be better to do a quotient rule on this one, right? And c is just a number, so a constant, right? So derivative top is 1. Leave the bottom alone. Minus top left alone. Derivative bottom is 1. All over the bottom square. Right? Quotient. So what happens on the top? We get x plus c minus x. The x's cancel out. So we just get c over x plus c squared. Now remember earlier we said that the differential equation, the y prime here, is the y prime as long as x isn't 0. In this y prime, which they're the same, here we could let x be 0. Right? Here we could let x be 0. So that's the one we're going to use, which we'll see here in a little bit. All right. So anyway, that's going to go on this side. So there isn't really anything I can do with the left side. It's pretty much what it is. But I do see an x plus c squared here, so I feel pretty good about how this is going to maybe come together. Okay? We could bow tie this, but that would get messy because we'd have something cubed, and I don't see that over here. It would be smarter to just do a plain old common denominator thing. Take the top and bottom of this first one by x plus c. Because then that would give me x plus c squared on both those. So my top would end up being, I'll distribute this. So that'd be x squared plus xc, and then minus x squared, and then that'd be all over x plus c squared. So get a common denominator there, and then that's all over x. Well, I can tell those x squareds there are going to cancel. I got xc over x plus c squared. And then what do I do with an all over x? Invert multiply, right? 1 over x, which is going to cancel those x's there. And so, sure enough, I get c over x plus c squared. So that's some stuff we did back when we were doing those limit problems. We did some of these complex fractions where we had to get a common denominator, and we usually bow tie, which you could do. And then you would get an x plus c to cancel, so you end up with x plus c squared there. So you could bow tie there, okay? But I just knew I was trying to get an x plus c squared, and I saw I already had one, so I just thought that would be a little smarter. Okay? So I got a match. Now, it said verify that that's general solution. So there's a few points in there, I'm sure. One for doing your correct y prime over here, probably, and so forth. Show that all solutions contain 0, 0. Well, all you have to do is plug those in. This is your solution right here. So just plug a 0 in for y, plug a 0 in for x, right? And you get 0 equals 0, right? 0 over c is just 0. And 0 over 0 is always true, right? So all these solutions, in other words, you get a true statement, right? You put a 0 in for x and a 0 in for y. Or you could just say, if I put a 0 in for x, I get out a 0 for y. So that's got to be true. Okay? So that would be how you would show that. So we know, so you'll see when we go draw the graph at the end why they threw that in there. They always, a lot of times they're trying to lead you in some of these problems. One part leads to another, not always, but a lot of times, and they do try to help lead you through there. So right now on that one, you know that when you draw the slope field, the solution in the slope field, when you draw the solution, you better have a branch. That thing better be going through 0, 0. Because what they're just saying right there is all the solutions will go through 0, 0. Okay? All right, so we'll see that when we get to that part here in a second. Okay, write the equation of the particular solution. Now remember, the solution is what again? What's our solution?
For x over,
Yeah, was it x?
Yeah,
It was x.
X over X plus C.
Our solution is x over x plus c. Don't forget that now. The solution is the original function, right, in a differential equation. The solution is the original function. So y is equal to x over x plus c. Write an equation, write the solution that contains 1 and 2. So what are we going to do there? Plug it in, right? So we put a 2 there. Right? Don't get too caught up in all the fancy language and everything. Hopefully you're getting more comfortable with that. That's going to get more and more comfortable as we go along. But there's not that many options you have of what you can do. Write the particular solution. They already gave you the solution. It has the point 1, 2. 1 is x, 2 is y. I mean, there's just not much you can do with it, right? Other than plug those things in. Okay, so let's distribute this over to this side. That'd be 2 plus 2c equals 1. 2c would equal -1. C would equal -1/2. So the solution that contains, remember when we talked about the particular solution, we have the general solution of the differential equation, which has the C in it. But once we have an initial condition, you could call this an initial value problem right here, the IVP, right? It's a differential equation with the initial condition. So they give us an initial condition, and we can plug that in. So we get x over x minus 1/2. So that's the actual solution we would be graphing. Then, find what the slope would be at 0, 0. So now, this comes back from part A. Remember they said part A, every solution is going to have a point at 0, 0. So what is the slope at 0, 0? So, we have two different slope equations we could use. We have this one, and we have the one we did earlier, which was what? C over
X plus C squared.
C over x plus c squared, which now for us would be -1/2 over x minus 1/2 squared, right? Because we know c is -1/2 right now. So which one would we rather use?
The one with the C.
We have to use that one, right? Because we already said earlier, this one doesn't apply when x is 0. Okay? But this one will. So we put a 0 into there. -1/2 squared is 1/4, so we get -1/2 over 1/4. Invert and multiply. -1/2 times 4, which is -2. So the slope, so the curve, so the solution that we're going to be drawing later is going to be this solution, and at 0, 0, it's got to have -2 slopes. We just calculated it from the y prime. Okay. Write the equation of the vertical and horizontal asymptotes. Now, to be honest, this is almost easier after we do the graph, but there is a part of the graph we wouldn't know about if they didn't ask us this. So all of these things are leading down to helping us do part D. So we got x over x minus 1/2. This is our equation. Find the vertical and horizontal asymptotes of that equation. Well, the vertical asymptote should be easy. When x equals 1/2. Remember, vertical asymptotes is when you get like 6 over 0 or 4 over 0 or 7 over 0. Well, when you put a 1/2 in here, you get 1/2 over 0. So x equals 1/2 better have a vertical asymptote. Okay? How do we do horizontal asymptotes? And you can probably look at the slope field, but let's pretend we don't have that.
Y equals.
Well, they're y equals, right? But they're at infinite. At infinity. Their horizontal asymptotes are what is happening as x approaches infinity or negative infinity. They're limit problems. What is this going to do as x gets really big?
Approaches.
It's going to approach 1. Remember that? The high powers dominate. If I got $1 billion and I lose 50 cents, I'm not even going to pick it up, right? The minus 1/2 doesn't even matter. When x gets really big, this is basically x over x, which is 1. Or infinity over infinity, we could just say, that doesn't make 1, but we could say L'Hopital's rule. Derivative top is 1, derivative bottom is 1, 1 over 1. This is going to have a horizontal asymptote at y equals 1. Really good problem because it's bringing in a ton of different things that we've learned, right? And they all kind of come together here. But now, you could get this once you go down to the slope field. You can look at it, you can kind of see there's a horizontal asymptote at 1. Okay, but now we know we got a vertical asymptote at 1/2, horizontal asymptote at 1. So now we come down to here. The slope field, sketch both branches of the curve that passes through 1, 2. So that's the one we already had, we were just talking about. And so We know there's going to be a vertical asymptote, or a horizontal, vertical asymptote of 1/2, but let's talk about several things. So first of all, we know it goes through 1, 2, right? Because we got that right there. So if we just follow this, it's pretty obvious it's going to do that. Now, what it's not so obvious here is where it goes, right? I mean, to me, it looks like it might go right up to the y-axis. But we know better, right? That's why part C was so important. Because otherwise, if you do that, you're going to see they're going to overlap and they're going to fail the vertical line test, so you would have known there's a problem anyway. But we know from part C that at 1/2, there has to be a vertical asymptote. So I'm going to draw that in there. Okay? So this is going to go up and approach that. Now we also know from part A that all branches pass through 0, 0. So you might, if we, in most of the differential equation slope field ones we did, if I gave you an initial condition, you just would have drawn this and been done, right? That's all you would have drawn, right? You'd have just said, well, it passes through there, follow the slopes, there it is. So this one, we needed more information to, sometimes when you do that, you're not getting the whole picture. So we know this goes through 0, 0, but now if you're going to follow the slopes, which way would you go? Would you go this way? Or would you go this way? Well, we learned, that was another thing we already found in one of the parts, that for ours, the slope is -2. So when it comes through here, it's got to be negative. So it's going to come down by that asymptote, and then it's going to level off at the horizontal asymptote. So all those things became important. So that is and then of course, if you went to your calculator and you graphed that equation, that's what it would look like right there. Okay?
This would be a no calculator.
Well, was this no calculator? I think it was.
What's it may be used?
Oh, it did say it could
Not.
be used?
Like,
Yeah, I was going to say,
I don't know how to read it.
Well, if you ignore one word, then yeah, it may be used. That's all okay. Okay, so that's good stuff. Now, how many of those could you? I would say, when you're ranking the free response question stuff, that's a pretty tough one. But there's some of that I think we do. The verify, maybe get a few points in there. And don't forget, that's one where a lot of the different parts were dependent on other parts. But, even if you couldn't verify in part A, you could certainly still use this solution right here, plug in your 1 and your 2. You could have got part B even if you didn't get part A. Okay? And so that's often very true. And actually, you could have got part C, really, with the asymptote there. All right? Without getting part A and so forth. So keep that in mind. All right. Let's move away from that today. And then when we have some work time, if you still have some sample 1, sample 2, they're not really due until next Wednesday. So, that's fine, but we're going to be moving on to these other packets. Tomorrow, we're really going to focus in on Friday's quiz. But, of course, today's a little bit of that, too, because we want to do our last theorem here that we have. So,
How many packages will we turn in Wednesday?
what's that?
How many different packages?
The first 2. So the 2 that you have, the sample 1, sample 2, we're going to turn those in Wednesday, and then the last 2, this one I set out yesterday, plus the last one I give you, we'll hand those in. Okay? All right. But this is really our last, tonight will be really our last book assignment between now and the midterm.
Yeah.
Right? But there is going to be that take home. Right? So it's going to be, tonight it's going to be a book assignment, not real long. Matter of fact, you'll probably get it done in class, or come real close, and then just packets, and then take home. And I think I was going to give you the take home tomorrow, probably. Okay? So that's the weekend will be that, packets, and just getting ready for the midterm, that kind of thing. We'll hand in the take home on Tuesday. All right, so we had the extreme value theorem. So 3 of the questions are going to be the state theorems, right? So 1 is going to be this: if you have a continuous function on a closed interval, then you're guaranteed to have a max to min somewhere in there. The intermediate value theorem, again, if you have a continuous function on a closed interval, it's going to hit all the values between the endpoints, all the y values between the endpoints. But when you state it, you need to state it like this, not that way, right? But that's how you think about the intermediate value theorem. Okay, so the third of the theorems, and you guys already saw that in the packet, they were asking you about it, is the mean value theorem. Okay, the mean value theorem, which is right? The MVT. Now, mean in this case is like average, right? Average value is why it's referenced this way. So intermediate, we think between, it's going to hit all the points in between. Now, when I ask you to state these, I may not put them in this order, right? So just don't, make sure you understand which name is which, but it's kind of easy. Extreme values, max and min. Intermediate values in between. And mean value has to do with average. Now, notice the word differentiables in here. So 4.9, the title of section 4.9 says why differentiability matters. So we really want to talk about the difference there. And then you also notice it says it's continuous on the closed interval, so it includes the endpoints, and differentiable just between A and B. Now, it doesn't mean that it can't be differentiable at the endpoints. And differentiable, remember, means the derivative exists. So no sharp points, that kind of thing. It just means it doesn't need to be differentiable at the endpoints. It needs to be continuous at the endpoints and in between. But it doesn't need to be differentiable at the endpoints, it just needs to be differentiable between. And we'll talk about why that is. Okay? If it is differentiable at the endpoints, that's okay too, right? That's fine. Just a need. All right, so if a function is both those things, then there exists some number C on the open interval, so there's some number in between A and B, where f prime at that number is equal to f of b minus f of a over b minus a. And what's f of b minus f of a over b minus a? Well, no, it's not derivative. F of b minus f of a over b minus a is what? It's the slope between the two endpoints, right? A and B in this are the endpoints, right? So it's the slope between the endpoints, right? And f prime of c is what? Derivative, but in terms of slope. It's a slope at. You can't do rise over run if you only got 1 point, Connor, right? You can't do rise over run at C because there's no rise, no run. It's only 1 point. It's the derivative. It's the slope at C. It's instantaneous rate of change compared to average rate of change. That's where you get the word mean in there and average. Okay? What it's saying is that if this function is continuous on the closed interval and differentiable in between, then there has to be some point in between there where the slope at that point is equal to the slope between the two endpoints. Another way of saying it is, if I go from Kearney to Grand Island and I average 60 miles an hour, there had to be some instant where I was going 60 miles per hour. Sometime my instantaneous rate of change equaled that. From a math picture standpoint, it would be kind of like this. If I have a function that's nice and smooth and differentiable the whole time, the average rate of change, the slope between the endpoints would be this. There has to be at least 1 point. Now in this problem, there'd be a couple where the slope equaled that. Okay, so if I average 60 miles an hour between here and Grand Island, I'd probably slow down some, go through those towns, but then I'd probably sped up sometime. But there had to be some time that I went. It's almost like the intermediate value theorem with rates. Right? You had to pass through. If you average 60, you had to pass through going 60 at some point. It might have been a little above, a little below, but you had to go 60. They tell the old story problem that goes with this, which is, and I think it might even be in one of your book problems today, is the, if you've ever been down to Kansas, they have a lot of toll road. You've been on a toll road where you go through a toll booth. And, well, you drive through and they give you a ticket, and then when you exit, you go through another one and they punch that ticket and they can tell where you got on and how far you've driven and they charge you for that. And the idea is, like we got all these people that drive through Nebraska, right? And so forth and wear down our roads and then Nebraska taxpayers pay for those roads. Well, they figure why not?
Our roads are way nicer too. Than
Where?
Because we went all the way to Ohio and then every state that had toll booths and stuff, the roads were just crap.
Yeah, it's amazing, and they do that with that. Well, I don't want to get political, but anyway, so yeah, it's amazing when you cross the state line and all of a sudden the road just totally changes, and it's bumpy and crappy and whatever, potholes and stuff. But the idea behind it is, why not let the people actually using the road help pay for the upkeep on the roads? So even people that live out of state, whatever, keep up and help keep up. But so the story goes, you come to the toll booth, you get your ticket punched, and let's say it's 2 o'clock, and it's it's got the date and the time and the where you're at, whatever, and then you go an hour down the road and you stop at the next toll booth and they grab your ticket and they stick it in the computer, and let's say it's now 3 o'clock, you've been an hour, and this particular toll booth is 80 miles away. So what's that mean?
Trouble
Average.
It means 1 hour. There's 2 o'clock, 3 o'clock. So you average 8, so the computer, right, as soon as it sees that, would know that you average 80 miles an hour, so then they tell you your charges, and then they hand you a speeding ticket, right? And, and they didn't witness you going 80 miles an hour, but I could just see these toll booth operators are making, I'm sure, lots of money. And they say, well, I'm sorry, but according to calculus and the mean value theorem, we know you had to be going. You had to be going 80 miles per hour at some point. No, I don't. Like I said, yeah, that's the story. That's the story. I've never seen that happen, so I don't think that would happen. But I think there's might be a problem in one of your homework assignments like that. But that's the idea, right? So now let's talk about
an example of it's not differential.
Yeah, I mean let's talk about what this means and why it has to be that way. So now remember, differentiable means, we're going to talk about differentiable a little more here in a minute, but differentiable means basically that the derivative always exists. So you can't have sharp points in it, right? That's one example where the derivative doesn't exist. Of course, if you have a gap or a break and the function doesn't exist, the derivative wouldn't exist either. That's all differentiable means. The derivative exists, right? To differentiate means to take the derivative. So differentiable means able to be differentiated, right? Able to take the derivative. The derivative exists. So that's what differentiable means. Now, it also means, if it's differentiable, it turns out, if you know a function is differentiable, it's also continuous. It's kind of like the square and the rectangle. We'll get to that in a second. But let's first talk about why differentiable has to be in here. Here's an example of one that's not differentiable at this point. It's differentiable everywhere else, but not at this point. Well, here, the slope between the endpoints is that. Is there any place on here where the slope is that? There's nowhere, because right here there is no slope. I mean, we could draw lines all over the place at that point. There is no tangent line at this sharp point. And the slope here is that, the slope there is that. So there isn't one, okay? So if it's not differentiable, it might not happen. Now remember, just like we talked about before, if you don't get an A, you might still get the car, right? So if a function's not differentiable, it still might happen. Like, so here I drew an example. This function between here and here is not differentiable because right at this point, right, the derivative doesn't exist. But if I look at this one, there's a point over here that would have the same slope. So it's possible you don't get an A, you still get the car. It's not differentiable. There still might be a point that has the same slope as the slope between the endpoints. But it wouldn't have to be. It's not promised to be. Okay, so if you have a nice, smooth, no sharp points, curve, then this is going to hold. Okay, this is the conclusion to the mean value. Now let's talk about why these endpoints aren't included, right? And why these are. So if it's continuous, right, it has to exist everywhere. We couldn't have we couldn't have an open circle here. We couldn't have this be undefined because then there would be no point to do the slope between their endpoints. That point might be down here somewhere, right? Maybe that point's down here. If you do the slope between those endpoints, it's possible there is no other point here that would have that slope. So we can't have an open circle. We've got to have these filled in. Okay, so this has to be a closed interval. Okay, it's going to be continuous, and those endpoints have to be there as well. Now, why don't we care about it being differentiable at the endpoints A and B? Well, let's just continue this curve here. Let's say there was a sharp point right there, right? We don't really care that there's a sharp point right there, right? The slope between the endpoints would still be this, and it's smooth everywhere in between there. That's all we need to guarantee that there's going to be a point that will have that slope between the endpoints. So we don't care if there's a sharp point at the endpoint. That wouldn't bother us. Now, if there's not a sharp point, that's okay too. But if there is, we don't care. So that's why we can't say it has to be differentiable on the closed interval. Okay, because it doesn't have to be. If there's a sharp point there, it would still be okay. All right, so when you write it out, we have to write it out this way. So if you had a function that was differentiable on a closed interval, which means it would also be continuous on that closed interval, then that's good. The mean value theorem would hold, right? Because you not only have this, you even got a bonus. You got the endpoints too, but you didn't have to have it. All right, so that's mean value theorem. We'll do a problem here in a second. Let's just talk about continuous and differentiable. So the word I like to use for continuous is connected, right? Now we know we have that formal definition, those three things you have to be continuous. But basically continuous means it's connected. No breaks, no holes, that kind of thing. But differentiable means it's not only be connected, it's got to be smooth. No sharp points. Okay? So it's kind of like the rectangle and the square. Every square is a rectangle, but not all rectangles are squares. Every every differentiable function is continuous, but not all continuous functions are differentiable, right? I got two here that are both continuous, but only that one is differentiable. Okay, so the term that's used a lot is differentiability implies continuity. It's kind of like square implies rectangle. If you got a square, you know you've got a rectangle. Okay, if you got a rectangle, it might not be a square. So differentiable function is automatically continuous. Continuous function might be differentiable, might not. Okay, so sometimes in the directions you'll just have, hey, you've got a differentiable function. They tell you the function's differentiable. You know automatically it's also continuous. Okay, it's got to be. All right, so the type of problem you might have, the very basic problem would be one like this. So let's think this through. You've got this function on the closed interval 1, 4. Find the value of C that satisfies the mean value theorem. And again, the mean value theorem would be, I'll just help you get started. Basically, the conclusion of the mean value theorem is this right here. Slope between the endpoints, there's got to be some point in between them. Your job is to find that point. Okay? Now, it would be good if this was a pre-response question and it said, tell why this satisfies it too. You would say, because this is a polynomial function and it's always continuous, always differentiable.
So do you do like a solve?
Well, yeah. Well, let's just go through it. I mean, it's not hard. It's not hard. It just,
56?
this is the function. This, I mean, you've got to memorize this, right? I mean, you've got to memorize the mean value theorem. So you've got to know this little formula here, right? So all you do is plug your endpoints in. So how are you going to do this side? What's f of 4? 57? Well, okay, Caleb's got the bottom for us, okay. What about the top? What's 57 minus, what's f of 1?
0.
0. Caleb?
3.
That way. All right, 57 divided by 3 is 19. Okay, now what?
Set it equal to the derivative.
Set what equal to the derivative? 19. The derivative would be 3x squared minus 2x. Now, technically, we should probably write that as
Well, wouldn't it be
c.
just 3x squared minus 2?
Yeah. That would be a dumb mistake to do all that work and then do that. Equals 19, right? So 3x squared minus 2. Now, technically, we're finding c. But if you did it as 3x squared minus 2 equals 19 and solve that, I would have no problem with that. That'd be fine. If you called it x instead of c, it'd be fine. So, but 3c squared would be 21. C squared would be 7. C would equal plus minus root 7, but it's from 1 to 4, so we would just take that. I think that is in between 1 and 4, right? Root 7 should be between 1 and 3. Okay? So, that's it. So well, it's going to be, right? Because the mean value theorem guarantees that so you did something wrong, right? So the mean value theorem guarantees that since the slope between these two endpoints is 19, there has to be at least one, there might be more, place where the slope is 19. And we found the one place where the slope is 19. So that's easy. Do the derivative, set it equal to whatever the slope between the inputs is. It's not hard at all. Now, one last thing. You don't have to write this one down because you won't have to do this, but I want to show it to you just real quickly. The value, no pun intended, of the mean value theorem and these other theorems, and the reason we do them is this one especially, the mean value theorem can be used to prove a lot of the things that are important to us in Calc 1. Think about the chart. We've used it a ton of different ways for a lot of different interconnections, relationships, and the whole point of the chart is connecting f and f prime. Then we also connected f prime and f double prime, which is the same connections, which allowed us to connect F with F double prime. So the whole key to all of that is connecting F with F prime. Well, if you look at the mean value theorem, that's what it does. It gives us an equation that connects F and F prime, an actual formula. So a lot of those connections can be proven using the mean value theorem. So, for example, if you read that, that basically says one of our very, elementary chart ideas. If F prime is positive, then F is increasing, right? But now mathematicians, they don't like, that makes sense. If F prime, which means slope, if slope is positive, this got to be going up, so the graph's going to be increasing. Now, mathematicians, they need more than that, right? They want a proof. They want something very specific. Well, here's what it would look like. All you have to do is start with this. Start with the mean value theorem. Since we're going to assume, I would have put up here that the function is differentiable. So the conditions are met. It's a differentiable function. Okay, well, actually, I don't even need to put that there because that says it right there. If F prime is positive for all x in the interval, then that means the derivative exists. If it's positive, it must exist. So that tells you the derivative exists everywhere, so it is differentiable. Okay, now I'm going to multiply the b minus a over here to this side. And I get this. No, you don't have to write this down. Okay, so this would have to be true, right? Now I'm going to flip it around. Well, I don't have to flip it around right now. But they told me in the given part, the if part of this, that F prime is positive. So I know that. What can you tell me about B minus A? It's got to be positive, right? Because, just because my interval goes A to B, right? So B has to be bigger than A, right? B is the right edge. A is the left edge, so B has to be bigger than A. So B minus A has got to be positive. Okay, so these are both positive. So that tells me that f of B minus f of A has to also be positive, right?
Yeah.
Which means greater than 0, right? So f of B minus f of A has to be greater than 0. So that basically tells me that f of B, if I add that over, has to be greater than f of A for all x in there. So in other words, no matter what interval I pick, if f prime is always positive, the y value to the right is always going to be bigger than any y value to the left. So therefore, that's the definition of increasing, right? Any y value on the right is going to be bigger than a y value on the left, so therefore the function is increasing. So we just proved it. It's just a simple little proof. It's basically just rearranging that equation, okay? But because we know the mean value theorem is true, that proves that for us, even though it seems kind of trivial to prove, but it's, okay? So that's a mathematical, a theoretical use of the mean value theorem as well. All right, so for your homework, let's work on, and it doesn't take very long. They worked for 20-some minutes, and they were pretty much done with most of it. And then exam 2, that's this one here. Now remember, the first two I gave you said sample, great big at the top. We call those sample 1 and 2. This just says exam 2 right here. So make sure you grab one of those. I know a lot of you did already. I'll just put it right there.
How much do we do?
Just get started. Just get started. A little bit of that first section, maybe. We got these other things going on. I would say it wouldn't be bad when you have exam 2 done by the end of this week. And so then over the weekend, you got the take home. You could be starting to work on exam 3, the last exam. But remember, we got Monday and Tuesday. We'll probably be working. Monday and Tuesday, we'll be working on that last packet quite a bit, probably. So
this one will be turned in all day.
not till the last day, the Thursday. But this new packet, if you had it done by the end of the weekend, maybe is fine. No hurry, really. Just work steadily on it. Try to work a few.
I would go
This is like,
What?
Which on the homework sheet says number 1 through 5 odd. Which set of those is odd? Is it 1 through 5 or 1 through 5?
It says 1 through 5 followed by odd.
It's even, yeah.
Then those are the ones that are odd. Well, I don't have my sheet here.
I'll take what I can do.
Hey, Mr. Clark, what's the definition of an odd?
1 through 5 odd.
Not going to.
Oh, shoot. 1 through 5 is odd, then 8 through 11 you do all of them.
Mr. Park, I'll be gone on Friday. So should I do this tomorrow then?
When?
What?
Maybe we can do it after. Like during lunch, maybe it's right after class we started.
Tomorrow, yeah. We could probably start it, the last half of class.
I'm also going to be on next Thursday, just the second midterm.
What's going on?
It's a Hastings honor orchestra.
So I'm gonna be missing some other people too.
I don't know, and Ryan might be gone, but and we're getting the details tomorrow, right?
And then you say,
You'll be here tomorrow.
whether the first one.
So Ryan, you were gonna do that tonight after school? Okay.
And then you say whether.
So one is, if it's cloudy, then it's raining.
Colin, when were you gonna do that?
Supposedly we're not leaving until after first block on Friday, so I might just come in and take it with the rest of your first block
Oh,
instead, so that might be easier, so.
yeah, that'd be great. Okay.
What's
Uh-huh.
the definition of a theorem? Like what is it? Really focus. Because you were known for being